we are working our way through, and hopefully we'll see if we can do this. I'd like it to happen, that we finish 14.6 today. And the first one is basically an overlap. We're going to go and just do another, calculate the value of a directional derivative at some given point. The one I've decided to choose is a fourth dimensional situation, three-dimensional function, and that would be the fourth one. And it's x, y squared e to the z, and the direction is from P to Q. So the first thing you're going to do is find out what the direction that you're going to get the thing, and it's going to be PQ. And second, take away the first, second, take away the first, second, take away the first. But we need a unit vector in that direction. And so I need to find the magnitude of PQ, which is 1 plus 4 plus 1, which is the square root 6. And so to get the unit vector, it's going to be 1/6 that vector, and 1 over root 6, I should say. So it's going to be 1 over root 6, 2 over root 6, and 1 over root 6. And we typically just leave these things alone. So we should then move on to getting the gradient function. In this case, we just add another dimension. So it's a derivative with x, then with y, and finally with z. And if you do this one with x, you get y squared e to the z. If you do it with y, you get 2xy e to the z. And if you do it with z, you get xy squared e to the z. And we evaluate the gradient at this point here. So that's going to be at 1, 2, 0. And that's going to be, that's x, that's y, and that's z. So y squared gets me 2 squared e to the nothing, which is 4. That one gets me 2 times 1 times 2, which is 4. 4 e to the nothings is still 4. And this one gets me 1 times 2 squared, which is 4. Oh, I didn't think I would do that. But we get 4, 4, 4. That's kind of nice, right? It's symmetry to it. And so the directional derivative of u of this function at the point 1, 2, 0 is the dot product of the gradient at that point with the unit vector. So it's going to be 4, 4, 4, and the unit vector is 1 over root 6, 2 over root 6, 1 over root 6. And those two get me 4 over root 6. Middle one gets me 8 over root 6. Last one gets me 4 over root 6, which I believe gets me 16 over root 6. And that one might be worth fixing. If you take 16 over root 6 and you rationalize its denominator, you get 16 root 6 over 6, and that partially cancels, and I believe you get that one. So your directional derivative, if you are at the point 1, 2, 0, and you go in the direction that this vector is pointing towards Q, the slope of that part of the hill would be a positive 8/3 root 6. So you're going uphill in that direction. Are we comfortable with the process for finding directional derivatives? Right. It's the gradient times the gradient dot product with the unit vector of the direction. If we are good with that, which I hope we are, we can now move on to our second topic for today, which is in what direction is the maximum rate of change, and what is the value of this maximum rate of change? So this would be, if you imagine the analogy that you're on the surface of a hill, what direction should I go to go the steepest, right? The magnitude, the greatest uphill, right? And how steep would it be for me to do that? So can you imagine you're on a hill? Isn't some hills, that direction is really steep, but if you go at 45 degrees, it's not so steep. If you go at this, you know, it's not steep at all. We'll show you a very basic way. Contour map of a surface, right? Can you imagine this is a surface, right? And we are interested at this point here. So can you imagine this here is P, okay? Now, if you take this point here, this curve, right? So, and you draw a tangent line, it looks like that. And if you draw a guy that's perpendicular to it, it goes like that. Are you comfortable with my orientation, right? Would you agree that any point P on that surface, isn't there going to be a tangent line, this green one going here, and isn't there going to be one at right angles to that? So far, so good. Now, what you might not know, and I'm about to tell you, but you see this vector here, this direction vector? He is actually, that's the direction that the gradient vector points in. Interesting. Now, do you see the one that's at right angles, that tangent one? That's the direction that you would have to travel if you wanted to walk round the belly of the hill. In other words, you didn't want to go up or down. So what that means is that if you want to ask the question, in what direction is the maximum rate of change? Here it is. The maximum rate of change. And I should put the vector of the maximum rate of change is in fact just the gradient at the point, you know, P. And in fact, haven't we already calculated that when we do directional derivatives? Isn't that one of the things you calculate, right? The gradient at the point P. Well, that vector is actually the vector that represents the maximum rate of change. And now, when they ask you, if I can find it here, what is the value, right? So how steep is steep, right? If I'm on that hill, am I going to go up at 10 feet, you know, for every inch I go, you know, 10 feet up for every inch, every foot forward, or is it 100, or is it 2? The magnitude of maximum rate of change is just that guy. So if you find the gradient at the point P, that vector is the direction that you go, right? The vector is a direction, right? The direction that you go to go the steepest on that surface. And what's the magnitude of it? The magnitude is the magnitude of that vector. So if that vector has a magnitude of √20, that's the maximum steepness that you could ever go at that point on the hill, right? And some points in the hill won't that be a lot less. In other places, it could be a lot more. And we say absolute value because we're talking about, it's all to do with perception. See, if you go this way, wouldn't that be the maximum downhill you could go? Right, so that would be negative and it'd be the same number but positive. So we stick to positives. We talk about the maximum. Right. Now, how do we get, because sometimes they ask you in what direction is there zero or no rate of change? In other words, you're walking around the belly of the shape. Well, that's a little bit tricky. So imagine I found out that that guy there was delta F, right? Okay. Then if you wanted to know the zero, I don't know what else to call it right now, so I'll just call it the zero rate of change guy, right? That guy would be the zero rate of change, or that guy would be. Has anybody got any idea how I got that by only knowing this? How can you get from here to here? Okay, notice what I've done. What would the dot product of 3, 2 and negative 3, 2 get you? Oh, shooting space. Forget what I just did there. I forgot a very obvious thing. Now, that's why I was seeing puzzled faces, because nobody could figure out why the heck that was the right answer. Do you now know why that's the right answer? Can you see the connect?
It's the orthogonals to going uphill.
They're orthogonal, and isn't that what's going on here, right? So if you know this one, there are 2 correct answers. Don't you just switch the digits around and make one of them a different sign? And couldn't it be the first one you make a different sign or the second one? Doesn't matter. That's why there's 2 answers. And if you're wondering why there's 2 answers, isn't one of them the guy that goes this way and the other one's the guy that goes that way? And so that's the reason there's 2 answers. Okay, let's put that into effect. I'm going to pick a function and I am going to find the direction for the maximum rate of change and then what that maximum rate of change would be. So let's see where the questions are. So they start at 18. Let me see how many of these there are, so I can put down a little list of them. So it's going to be question 18 to 23, right? So that's where the type of question I've just spoken about happens. So here's a version of question 18. The function that we're going to deal with is 8xy squared. The point P is 7, negative 5. Have you noticed that in this question, there is no U? There is no direction vector to be calculated, because that's not what we're going to be doing. What we're going to do now is we're going to find the direction, the vector of the maximum rate of change. And that involves us finding the gradient vector first. If you differentiate this with respect to x, you get this guy. And if you do this with respect to y, you get that guy. Then think of that as your x and y coordinate. So when you do the direction, the gradient vector in that direction, guess I should have put numbers there, but too late now. 8 times negative 5 squared, 16 times 7 times negative 5. I'm just looking at the answers here because I want to check it out. This number here, okay, is 200. And this guy here is negative 560. Does that look accurate? Right. And so that is the direction that you should travel to get the maximum rate of change. Now, what is the maximum rate of change? Well, that's the number, the maximum rate of change. I'm going to have to figure a way of abbreviating this. Isn't it just the magnitude of that vector? So it's going to be the square root of 200 squared plus negative 560 squared. And I'm going to cheat because evidently it simplifies down to 40 square root of 221. And you're just going to take my word for it because I ain't going to do that calculation, right? But evidently that horrible number can be rewritten as 1600 times 221, and that's where that came from. Are we good with this question? Because in a way it's a lot less work, isn't it, than directional derivatives. Find the gradient at the given point, and that gives you the maximum rate of change direction. Find the magnitude of that vector, and boom, you got that again. They didn't ask it in this question, but let's pretend they did. The third and final question that they might ask you is, what direction should you go to get zero rate of change? So zero rate of change. Well, don't you take this guy, switch the order, and change one of them. So if you switch the order, wouldn't that be one of the correct answers? If you switch the order and you change the sign of one of them, wouldn't that also be correct? And if you want to check, shouldn't this guy dot product with that one be 0 and this guy dot product with that one be 0? Another way of checking, isn't that one the negative of this one? So, you know, pick whatever one you want. Maybe you'll switch places first and then decide which one to do negatives. So if you switch places, you would do negative 560, 200, and then I decided to make that one negative. Or you switch places and you get negative 560, 200, and you decide to change the negative 560, in which case you get that answer. Interesting. Now, I like the analogy of a hill, but that isn't the only thing. Can you imagine that these functions might represent, you know, the value of this function represents the temperature at a given point on a plate, right? So you're looking at heat distribution. Then if you want to go in the direction of where's the heat coming from, isn't it coming in, it's coming from that direction. So if you had a model that represents, you know, the temperature at any given point X, Y on a plate, right? And it was given by this formula, wouldn't you be able to predict where the temperature is coming from, where the heat is coming from? At any given point, the hottest direction to travel would be this one. And that to me would mean, oh, that's where the heat's coming from. Any questions about that? Are we good? Move on, do another one. Okay, next guy, let's pick something that's not as clean. 19 doesn't look very clean, so I'm picking that one. It's a rational function. We're interested in the point negative 5, 5. And it's the same two questions again, maximum rate of change and what the direction is. So I'm going to find the gradient vector first. If you want to differentiate this function with respect to S, or for that matter, with this function with respect to T, I think they're ugly enough to be done at their side. So I'm going to call this guy F and I'm going to call this guy G because we want to find a derivative, partial derivative with respect to S. So it's going to be F dash G take away F of G dashed all over G squared. Right, if you differentiate that with respect to S, you get 1. You leave this guy alone. You get that. Take away, you leave this guy alone, you get S. And if you differentiate this with respect to S, you get times 2S. And the whole thing is over the bottom squared. What do I get? I get an S squared plus a T squared, take away 2T squared. So that basically ends up being T squared, take away S squared over that one. Are you comfortable with that question? Does that look good to you? Okay, so over here, I'm going to put T squared take away s squared over that guy squared. Now I'm going to do the same thing, but I'm going to do the derivative with respect to t. Now, there's only one t in this expression, it's on the bottom. Could I do it as a quotient rule? The answer is yes. And there's nothing wrong with doing it as a quotient rule, and it works fine. But I'm going to do it a little bit differently. I'm going to call this guy s times s squared plus t squared to -1. Now, if I write it like this, then if I want to differentiate with respect to t, isn't this basically a chain rule? So if you think of it in that sense, you multiply by the power, which is -1, and then you reduce the power by 1, which is -2, and then you finish by differentiating the inside function, which is this guy, with respect to t, which gets me 2t. And these get multiplied together to give me -2 st. And this guy goes in the bottom. And he's squared. Are you comfortable about that one? Does that seem reasonable? Okay, so back to our question. This guy here is -2 st over the same ugly bottom term squared. So I'm going to get the direction of maximum rate of change. I think I'm just going to call it direction now. And that's going to be the gradient vector evaluated at this point here. So it's going to be -5 squared, take away 5 squared over -5 squared plus 5 squared, all squared, comma, -2 times -5 times 5, and over, this guy's going to be over, the same as that guy really, squared. 25, take away 25 is nothing, so I won't do any more on that one. That times that is positive, that's going to get me 50 on the top. 5 squared's 25, 5 squared's 25, that's 50. 50 squared is 2,500. Those simplify down to, I believe, 150. And so that is our direction vector. What's the size of this? The size is the magnitude of that vector, which is not that hard to calculate, isn't it? 1/50th. If there's only one component, then the magnitude is the same as the positive value of the other component. But you can do, 0 squared plus 1/50 squared and all that stuff. But eventually you'll get that. Are you comfortable with that? The direction of the maximum rate of change is this. Oops, is this guy. And the value, the magnitude of it is this guy. If they wanted to know, again, they haven't asked for it yet, but if they want the direction of 0 rate of change, wouldn't it be, in fact, wouldn't it have to be that one? Or would it? That one works. Would you agree that one works? Is there any other direction that would also work?
Would it be just 1/50th 0?
Wouldn't 22 0 and my favorite number 42 0 also work? If you do 0 number 0, won't you always get 0 from the dot product? That's very rare, right? So normally there's two answers, right? The one you get and the negative of the one you get, right? That's the two typical answers. But I guess this is an exception. And interesting that that happened. Are we getting more comfortable with that process? you want to see one more, or shall I move on to the last piece? Not an awful lot. I'll do one more then. We're having a function. And we're interested in, oh, we're interested in a bit of everything here. Okay, that's cool. So in question A, they want the direction, right? So the point P is 5, 4, 5, and they want us to find the direction derivative. And the direction that we're going to go is 1, 1, -1. So this is basically Friday stuff, right? For this function, find the direction directive, find the direction vector, right, derivative at that point. And I just noticed something I'm going to have to do. Isn't that vector not a unit vector? And we need unit vectors. But isn't its length the square root of 3? So is it okay if I just do this in my head and write down the correct unit vector to use? Are you comfortable with that? Or do you need to see the work? The magnitude of that is 3, so this is a unit vector parallel to that one. Okay, now I'll do the gradient vector. Actually, not a bad one. It's x, it's y, and it's z. In this case, if you differentiate with x, you get e to x. You do this with x, you get -3y. If you do this with x, you get yz, comma. If you do it now with respect to y, you get nothing. You get a -3x and an xz. And if you do it with respect to z, you get a nothing, you get a nothing, and you get an xy. So we've just found the gradient vector. And now I'm going to evaluate it. This guy, 5, 4, 5. This guy x, call this y, call this z. So let's see. 8 times that guy, 8 times 5. Take away 3 times 4 plus 5 times 5. It's a bit messy. Middle one, -3 times 5 plus 5 times 5. And the last one is just 5 times 4. That's 40. Take away 12 is 28. 28 and 25 is 53. That's 25 take away 15, so that's +10, and that's 20. So we have now found the direction vector for the maximum rate of change. Go in that direction if you want to go up the 4th dimensional hill in the steepest direction. Okay, so that's actually question B I've answered. Now back to question A. If you want to find the direction derivative at the point 5, 4, 5, it's the dot product of that guy with the unit vector. So it's 53, 10, 20, dot product, one of these guys, one of these guys, and minus one of these guys. So that's going to get me 53, 63, 43. So evidently you're getting that, which is 43 root 3 over 3. That's the answer to part A. Tell me the direction derivative. we got part B already for free, so that's the direction of the maximum rate of change. And part C is, and what is the maximum rate of change's value? Well, won't it be the magnitude of this vector? Which means it's going to be the magnitude of this guy, which I'm going to cheat, which evidently happens to be 2 the square root of 701, and that's because they told me it is. Are we good? So what we've got left to do here, move this over here, is a couple of puzzle ones. They're basically questions 23 and 24. I'm going to do question 24 because 23 is just like it, but with different numbers. And it's also called a tutorial exercise. So that means you have to put in the work in. So here is the function. It's pretty nondescript hill. I'll just read out the question. It says, find all the points which the direction of the fastest rate of change for this function is the vector 1, 1, 0. So we're trying to find all the points on a surface where if you go in that direction, you're going the steepest. Right, so evidently there's going to be a lot of points on the surface, and we are going to try and find out what an equation that represents all those points. That seems impossible because there doesn't seem to be a lot of information, but nonetheless, we're going to try it. I know the maximum rate of change is this guy, but normally we know X and Y because we're finding the maximum rate of change at a given point, but I can still calculate that guy. Is the derivative with X and the derivative with Y. And if you do an X with this guy, you get 2X take away 4, and then you get a 2Y take away 6. Are you comfortable about that way? I found a gradient vector. Now, what do I know about this gradient vector? It's not a 3-dimensional, it's just 2, so it's 1, 1, right? I know that it's that guy. So I know that this fella has to equal that fella. Do you see where we're going with this? Actually, I'm not sure I can see where we're going with this because I'm about to solve this question for one unique point. I'm about to do this. Oh, okay, I know what's going on. Isn't this just one possible version of this vector? Because wouldn't 2, 2 be the same direction, just twice as long? And 10, 10 would be the same one, just 10 times long, and so on. So that means I'm going to replace this guy with this. That gets me out of the problem that I had. If I just left it as 1, 1, I'd be able to tell you one single point, which is doable. I could do that. But I'm now going to call it K over K. And now we're going to try and see if we can solve this equation. Now, technically speaking, you're not going to solve it like X is 2, Y is 3, and K is 7. We're going to solve it a totally different way. If you have these two equations, which I'm going to call number 1 and 2, If you take equation 1 and divide it by equation 2, you're going to get 2x take away 4 over 2y take away 6 is k over k. Are you happy about, as long as you do it to both sides, it's okay rule being used in a very strange way? Right? If this is equal to that and this is equal to that, then those two guys divided should be equal to those two guys divided. That's kind of the lunch. But wait a minute. Isn't k over k 1? We'll assume 0 doesn't work because that would be 0. Would be weird. Now, we're being asked to find all the points, which really means we're being asked to find an equation, y equals. Can anybody see how we could get from here to a y equals kind of formula? What would I do as my next piece of algebra? And if it helps, how about doing that? What shall I do next?
Just move the 2y minus 6 to the other side.
Is it that kind of thing you're talking about, Christian?
Yeah.
Yeah, agreed. Remember, the goal is y equals. So what do we do next?
Subtract the 6, or sorry, add the 6 to both sides
Looks good to me.
and then divide by 2.
And do you know what? It's the correct answer because I have the answer here, not the working. Right? Sneaky. But can you imagine a surface, right? And can you imagine looking at it from the air down and there was this line called y equals x, right? Wouldn't that line y equals x follow the surface of the hill? And every single point on that line y equals x as it meets the surface, every single one of them, that would be the steepest direction. Now, I have no idea what that would be useful for, except if you were a crazy hiker and you just loved making your life hard, wouldn't that be the worst way to walk up and down that hill? It's like, what's the hardest way up? Actually, don't mountaineers do that? Don't they look at a mountain and say, no, you could walk up this side, but if you climb up this side, it's really hard. So I guess this is for mountaineers who want to find the hardest way to go up and down a hill. This equation would kind of model that situation. Are we good? Right, then we are finished 14-6. I'm pleased because that's kind of one of my goals. We have 3 sections to get done this week, but the good news is we've done one of them already. The bad news is the 2 that are to come are pretty scary. I like them. I like scary. So the next one we're going to do is 14-7. And 14-7 is solving maximum and minimum problems. This is the equivalent to Calc 1 optimization questions. You remember those questions? Find the biggest value of X and Y for an open fence that has the most square footage. Or remember the boxes without lids and you're trying to find the dimensions of the box with the smallest surface area or the biggest volume, or what other questions? Find 2 numbers that add up to 20, but when you multiply them, you get the biggest product. You know, those types of puzzles, optimizations. This is the big grown-up version of this. This is like the ultimate version of those same types of questions. And that means that we need a kind of intro to this before we get right into solving the problems. So here is my first intro. Oops, that's a Z. Let's look for local max, for local minimums, and see what they might look like in a 3D world, right? If you imagine a very simple surface that looks like that, would you call that a hill? I would call it a hill, right? Now, would you agree that that top dot there, even if I've drawn the thing badly, is a local maximum? You agree? Now, when you did Calc 1, where did you find local maximums? Well, didn't you find them when the derivative was 0? Wasn't that, they're called critical numbers, wasn't that the places you went looking, right? Now, when you look at the top of a hill, as we have here, you don't have one derivative, don't you have partial derivative with x and partial derivative with y? So what would this look like in that world? Well, can you imagine a line going parallel to the y-axis, and wouldn't there be another line going parallel to the x-axis? At the top of that hill, wouldn't those two lines have a 0 gradient? That makes sense? Now, what does that look like? Well, in our world, you want to find the top of a hill. Don't you have to solve when is the partial derivative with x equal to 0 and at the same time, right? Both have to be true, and the partial derivative with y, with respect to y, also has to be 0. Does that make sense that that's where the hills are going to live? Agreed? So we will find all the places where that's true. And those places where that are true are called critical numbers. Same term that you would use in Calc 1. So critical numbers are all the points where, and I'm going to write it like this. When you write it like that, doesn't that kind of force you to do both 0 at the same time? That's just a way of making you realize that that is what's happening. Now, what about the bottom of a valley? Would you agree if I save time, because I'm hopeless at drawing? Wouldn't at the bottom of a valley, wouldn't the same thing be true? Wouldn't the 0 first x derivative and 0 first y derivative? So if you're going looking for local max and local mins, don't they have to happen at places where this is true? Now, back in Calc 1, there are technically 3 things that could happen. You got a local minimum, and you got a local maximum. Can anybody remember what the third blinking thing was called? A place where the derivative was 0, but neither of those two happened. X cubed is an example of that. Had a big long name. I'll draw the picture for you. It would look like that.
Is it a vertical asymptote?
Oh no, I know what you're talking about. No, the volcano things. I'll start the word then. It's a horizontal. Something of something. A horizontal point of, oh, come on, finish it for me. I'm spoon feeding you this one. It's called a horizontal point of, come on, you get young, subtle brains. You should remember these things. I'm old, I forget everything. I couldn't tell you what I had for dinner yesterday. Come on.
Is it
Horizontal
convergence?
point of, Matthew?
Is it convergence?
No. Okay.
Oh, okay.
I guess I was asking too much. It's probably something that you only heard a few times. Now that I've written it down, is that some of you saying, oh God, yeah, I remember him saying that, right? No. Well, God, you're even worse than I am, Matthew. I'm sure I have said that a couple of times. Not often, that's true. Right. So you've got a minimum. Better put the terms in here. This is a local minimum. This is a local maximum. All right. And this is called the horizontal point of inflection. That's what you would get in the 2D world when you find the critical numbers, right? The places where the derivative is 0, right? Now, in the 3D world, right, you get a local maximum. You get a hill. You can get a local minimum. And you might think, well, that thing disappears. In the 3D world, you can't get anything that looks like that. And that's true, you don't, but you get something else instead. And you will remember this name. It's called a saddle point. And the reason you'll remember this name is, doesn't it look like a saddle? Now, at that point there is the saddle point. If you look at it from one orientation, isn't it the bottom of a little hill? From another perspective, isn't it the top of a hill? Doesn't it depend on where you're coming? If you're climbing down this way, isn't that place the bottom of a hill? If you're climbing from over here, isn't that place the top of a hill? Those are called saddle points. So what the problem that we're going to have to deal with is, if you want to find local max and mins, right, and maybe you want to find saddle points, isn't the first thing you're going to have to do is to find these two partial derivatives and find out when they're both equal to 0. And when they're both equal to 0, you're going to find a local max, a local min, or a saddle point. The problem is, which one of the three do you get? Can you pretend I did a question and I found out that when x was 1 and y was 2, that was my critical number? So at the point 1, 2, when you go upwards, it's a hill, it's a valley, or it's a saddle point. But we have to be able to tell which it is. When you did Calc 1, how did you know it was a local max, a local min, or one of these? And wouldn't you do, what, just graph it and look would be the easiest, wouldn't it? You know, just put it into Desmos and, oh, it's a big happy face, it's a minimum, right? Oh, it's a big sad face. Oh, it's a maximum. Oh, it's a funny squiggly line, snake. Oh, it's a point of inflection, right? You could do it that way. If you didn't want to do it that way, couldn't you do it by table of values? Just pick a number either side and see if it goes up and then down, or down then up, or up and still up. You could do it that way. In the 3D world, however, we have a test for it, right? And that's, do you know those movies that you get in 3 bits? And right at the end of movie 1, the hero is definitely going to die because the dragon's going to fry him. And then they cut and they say, wait until sequel 2 comes out. Wait till sequel 2 comes out. I am going to tell you the formula for figuring out which one of those 3 situations it is, but you'll have to wait until tomorrow to find out, unless you go and look up the textbook and cheat. No, it's not cheating, in case you just want to know early. Okay, so last name for attendance, please.